next we have Dr. Lee Orff, Professor at and Department Chair of Central Michigan University in Mount Pleasant, Michigan. He will be discussing a long-track, strong tornado simulation that he's been working on. It's a really, really cool video. I'm really excited for him to show you guys. Let's make sure it transitions here. Without further ado, Dr. Lee Orff.
Thank you, Allison, and thank you for inviting me to this. This is my first Valpo conference, the Great Lakes Conference here, and I'm very grateful to be invited. So I'm going to talk about a simulation that I've been looking at for about a year now. Before I get started, I do want to acknowledge my collaborators, which you can see here. Robert Wilhelmsen at the University of Illinois. He's retired now, but he still works a bit. Bruce Lee and Kathy Finley from the private sector. They work for WindLogix. So I am going to first start out talking about some of the motivation for this work. I mean, I'm a guy who really is into computers. I sort of got into weather both from the computer side and from the excitement of weather side. But the motivation for this particular study, then talk about the process we went through and then some results. So what we really want to do is simulate a supercell thunderstorm that produces a long-track EF5 tornado. It sounds pretty straightforward. Turns out it's a little difficult to do. Just like Mother Nature doesn't produce a lot of EF5s, neither do cloud models. Then I want to actually visualize this storm in a way that makes sense to human beings, enables comparisons to field studies, and also because models have the luxury of having all the data everywhere, actually look at what's going on in ways that we can't with remote sensing. And then do this multiple times. Right now I have one storm, which is exciting, but we want to do this for a lot of storms. So the large majority of fatalities occur in the strongest storms. They're the least common, but EF4, EF5 tornadoes about 90%. The longer the path, the more damage it can possibly do. That's pretty straightforward. Field studies have really helped us understand these storms more. One thing that comes up a lot is cape and shear. You've learned this in your class for sure. But if you look at the bottom photograph, that's a climatological photograph for a supercell that produces no tornado. The next one up is weak tornado. The top one, the solid line, is strong tornado. Notice the 0 to 1 kilometer shear is very long, and that where the hook is. And that is a key factor for these really strong storms. You have to have a lot of shear and a lot of cape. Until recently, we really haven't been able to do this kind of work simply because the technology wasn't there, but it's there now. So I've been trying to bang my head against the supercomputer, Blue Waters at the University of Illinois, which is a great machine, and it actually, bang your head long enough, sometimes stuff comes out. Maybe not what you want it to, but so anyway, we need a model first. We're using a model called CM1. It's developed by George Bryan at NCAR, and it, you can Google that, you can download it and run it yourself. You need to be able to manage an awful lot of data. These simulations produce hundreds of terabytes, petabytes of data if you let it. What you're seeing here took about 100 terabytes of data, what you'll be seeing me visualize. And you need a little bit of luck. Just like going on a real storm chase, right? There's no guarantee you're going to get a storm, certainly not a long-track EF5. Indeed, it took a lot of tries before we had this result. This didn't come easily. I'm hoping that I can hone my techniques and apply this to more environments because there have been a lot of really big EF5s lately. If you guys are interested in doing something like this for a living, or you're interested in it, computers are your friend. Learn Fortran, Python, Linux, Bash shell scripting, video editing, etc. And be a little bit obsessed. I know you're already obsessed because you're meteorologists. You all are kind of crazy about the weather. Anyway, so more specifically, so I configured the model with the May 24th, 2011 El Reno EF5 supercell environment. That's the first El Reno storm. Then you just grow a storm. You grow it. You have to kick it off. So we use what's called W forcing. We basically force an updraft and then let the cloud form, and then everything takes over. We didn't have it work the first time. I won't go into details, but it was, the model would, blow up, CFL, restart it, decrease the time step, that sort of thing. Then you go, look at this. And I'm still stunned that this actually happened. It's really an incredible simulation. And then I've been developing my tools for visualization, and you'll see the results. So what's this storm like? It's a classic or HP supercell. It's certainly not an LP supercell. You have a tornado on the ground for almost 2 hours. There's a lot of interesting things going on. This tornado spends most of its life wrapped in rain. Now, so what I'm going to do now, it might help to dim the lights a bit for some of the graphics. But the top graph here is the wind speed. So you're looking at the tornado forming here. Look at the scale here. This is 130 meter per second winds. The bottom scale is pressure. So you have blues here are 150 millibar pressure drop at the surface. These dark reds are getting into 130 meters per second. That's 300 miles an hour. Well, this tornado produces 300 mile an hour winds near the ground for, that's part of the storm lasts for like, almost an hour. So it's crazy. Now, a little disruptive event happens right about here where the an anticyclonic vortex sweeps in and gets sort of ingested into the tornado, and it causes it to weaken. It's only like it's still in the EF4, EF5 region, but it does weaken. And so here's the EF5 line. This is the cutoff for EF5, and these are the surface winds. So we're like way over the EF5 cutoff. This is just surface winds here matching the tracks. So it's an incredible storm. It's almost on the edge of, is this really, do we actually see winds like this? Well, we have seen winds exceeding 300 miles an hour from radar data. Get a lot of mesocyclones forming along the forward flank downdraft boundary, what we sometimes call the forward flank gust front, but it's really not a gust front in this simulation. There's a lot of interesting vortex dynamics that you'll see. And there's cyclonic interactions, there's anticyclonic, cyclonic destructive interactions, all sorts of things, and I'll show you a picture that sort of shows you just a snapshot in time. Is it possible to dim the lights? Okay, well it'll show up a lot nicer, but you see some interesting small scale stuff going on, some large scale stuff, and oh, very good. You guys will appreciate some of the detail that comes into this. And we've identified this feature we call a streamlined vorticity current that seems to be really playing a key role in maintaining the storm. And this is just a quick, you'll see a lot more of this, but this is what I'm calling the SVC. So here's a tornado, and these are just parcels being dropped right where I think this thing goes. It goes in. So you've got a lot of baroclinically generated horizontal vorticity being tilted into the updraft. So here's our sounding, lots of steep lapse rates, lots of big, fat, juicy, tall cape there. It looks like we should go chasing. Ridiculous parameters, storm relative helicity for like the bottom 1 kilometer, 0 to 1 kilometer is 360 meters squared per second squared, 0 to 2, 625. There's the boundary layer. It's pretty well mixed, but not too well mixed. We don't get those horizontal convective rolls, which actually are a problem in some of these simulations. And we're just kind of looking up the sounding, like, wow, let's lift the parcel. Where do we end? Well, here you bump into the tropopause around 150 millibars. So it's, here's the shear, though. There's that low, this is meters per second. Here's the shear at the lowest, like, 100 meters or so is incredibly high. And this is really characteristic of these super tornadic storms. You have very large amounts of low-level shear screaming, directional shear, almost like the sickle cell type photograph that people talk about sometimes. So, all right, here's where the fun begins. So here's the storm looked at from quite a far distance. This is just a volume rendered cloud image. So this is kind of what it would look like if you were seeing this storm. You can see a little tiny tornado there, which will come closer in a moment. What I'll do is give you a sense of scale. So here's the actual model domain, okay? So you're looking at 120 kilometers on a side, horizontally, and 20 kilometers tall. Okay, we got to fit that storm in that box, and we want to center it right in the middle of the domain because actually we have 30-meter grid spacing for the whole bottom 10 kilometers and centered on the storm. So it's basically an isotropic grid. And there's that little, what looks like a small tornado, right? We're trying to give you a sense of the scale. You have to model this whole thing, so you have to get the tornado resolved. Here's just another view. Here's sort of a close-up of the cloud field. Here's sort of like a satellite image. I tried to make what looks something like a visible satellite image. And I like the overshooting top and all the little cumulus turrets and stuff that you see. It looks kind of neat. Okay, now I'm going to animate the actual storm. So you're going to look at the cloud field and the rain field. So this is going to take a little while. This is an anticyclonic vortex. It does not really form a tornado. And keep your eye right about here. And there's the tornado condensation funnel, descends to the ground. You see a very, very interesting inflow along this region here, which is where I'm going to be focusing. I freeze the frame here. Look at this little rain curtain. So this is a curtain of rain. This has been seen on radar. You get these very thin, maybe even 50-meter across curtains of rain. They may play a role in vorticity generation. We don't know. Got a lot of data to look at. But this is run 60 times real time, just so you know. So 1 second of what you're seeing now is actually a minute. So even though a tornado is very fast, this is going faster than it really is. So you see all sorts of interesting detail, very, I guess you call it turbulent, unsteady downdrafts in the RFD region. We're looking at the storm from the southeast looking northwest. And it's amazing. You know, I can watch this for hours. I probably have. You know, did this really happen? You see, I'll slow it down. You'll see some more detail. But you see these horizontal rolls that kind of go up the storm. You see it's wrapped in rain now. Multiple vortices. It's basically got just about something for everyone. And it goes on. Now, the cloud, I am interested in making stuff like this where you're kind of trying to make it photorealistic. I use that term very vaguely. I don't really mean realistic, but something that you could convey. You could have a conversation with a storm chaser and they would be able to, oh yeah, I see that kind of thing when I'm in the field. Now we're going to focus on vorticity. I'll keep the cloud here just so you can kind of compare what's going on. So I'm taking vorticity magnitude and I'm coloring it by the vertical component. What that means is the red guys are cyclonic, the blue guys are anticyclonic. And here's the genesis right here. This little guy right here, this guy's going to grow into an EF5. Okay, so keep your eyes focused right here. If I had to pick a point where I say genesis begins, which is kind of redundant, it would be right there. So, but it takes 4 to 5 minutes before you actually see the condensation funnel make it to the ground. So what this tells me is, at least in this simulation, you know, if we could detect this and we knew that this was going to grow, we could actually produce a better forecast. But this is miles away. Here's that anticyclonic tornado. Or I'm sorry, vortex. It's not a tornado. The winds aren't strong enough. So here's the RFD. Here's you see consolidation of vorticity along this region. We see lots of warm RFD surges. So we have positively buoyant air in the cold pool. Seems kind of backwards. But so how could we get that? We haven't really done a lot of parcel analysis yet, but certainly adiabatic compression can warm the air. If you have strong enough downdrafts and you force the air down, it's certainly feasible. Although you'll see also it's very rainy in the RFD. Now these things that are going what's called vortex breakdown. Now it's a screaming EF5. Okay, now it's producing 120, 130 meter per second winds. I just freeze it just to sort of look at the structure of a tornado at this point. So this is the vorticity field. The red means cyclonic vorticity. And notice how it looks like a little pretzel. These are both, this is what's called a two-celled tornado. So there's actually a downdraft between these two intertwined cyclonic vortices, and that is consistent with the two-celled tornado model, if you look that up, from laboratory work and from other things as well. It's very difficult, obviously, to measure that in reality, but what our laboratory models and our numerical models have told us is that is reasonable. More juicy, warm RFD air over here, lots of vorticity. Sometimes it just gets swept into the tornado. The tornado seems to be like, you throw enough stuff at it, it just kind of is, you know, sometimes it's effective, but sometimes it's just like, all right, go ahead, throw some more vorticity at me, I'm just going to shove it up in the updraft. And it does a lot of that, and it's fascinating. I mean, I slow this down, because watch this guy, this has to be seen in slow motion. So this is an anticyclonic vortex that sort of forms out of the pool of anticyclonic vorticity. It gets caught in the tornado. You got a vortex wrapped around that vortex, which is wrapped around this vortex, which is getting curved around that vortex, and then this thing gets pulled up along the tornado, and it's fascinating. You wouldn't be able to see much visually if you saw this, but I have seen chaser footage where you get these horizontal rolls and you can see in the cloud field because there's enough of a pressure drop from the rotation that you can actually condense, just like a regular tornado. So these horizontal rolls are not figments, I think, of the model's imagination. I think they do occur in nature. And there's more warm RFD air. And then look at this. Is there a tornado in there? I mean, it's like a big spaghetti, pile of spaghetti. So you've got some anticyclonic vortices. You've got a mess of cyclonic vorticity. You know, when you look at Vortex Dynamics, I mean, it gets really crazy. I hope we don't have to be this good at modeling storms to forecast storms, because that would be really, really bad, because it's chaos, it's turbulence. But anyway, there's a lot that can be learned. So the cold pool undergoes all sorts of morphology. Notice that we have this secondary boundary. So here's like what you can call the forward flank downdraft boundary, like the one that's sort of classical and sort of laminar or smooth. Then you have these secondary boundaries, and these secondary boundaries seem to be the source of some of this vorticity that is important. So I'm just going to look at pressure now. So obviously a tornado has low pressure. You'll notice this thing sort of pulses a little bit. That's, I think, gravity waves. I think we do have a bit of gravity waves bouncing off of the top boundary, even though we have a sponge in there to slow it down. This blob, though, this is intriguing. This is a feature that's associated with the streamwise vorticity current that I'm going to be focusing on. So it's basically a horizontal roll that's sort of being tilted. You know, the tornado extends up. You can see evidence of a tornado with a vorticity field all the way up to the top of the model domain, about 18 kilometers. Now that's amazing to me. You don't see it so much in the pressure field, and this is, you know, I picked an arbitrary isosurface. This could go up higher. But the point here is the tornado is very tall. This is just the cold pool. So this is the coldest air. Here's all these secondary boundaries. So you get the first one, the second one, the third one. Here's like a fourth one. Here's the warm RFD. There's the tornado. There's the anticyclonic guy. But a lot of interesting structure here that we're trying to sort of unpack. This is vorticity. And during the genesis phase. So what's going on during the genesis phase? Well, okay. What I see is a strengthening of this SVC. This is what I'm calling the streamwise vorticity current. And a whole lot of vorticity consolidation. I don't know what else to call it. When you look at this storm from sort of the supercell scale, it looks as if there's like a perfect balance between where the updraft is, where the convergence is. It just seems like the updraft is just sucking everything into one spot, and really everything's aligned vertically. This is during the maintenance phase, so this guy is just crazy, you know, all sorts of stuff going on. You see these mesovortices that I'm talking about that form on the outside of this streamwise vorticity current. So you've got vorticity at different scales. This is the updraft, so this is just the vertical component of the wind. So here's the RFD, here's the big mesocyclone, you can see the tornado signature forming here. This is all the compensating subsidence from all this this vertical motion. Here's another view of, looks like the mothership, you know. This is a mesocyclone. I mean, that's a mesocyclone, no doubt about it, a rotating updraft. So I've been playing with all sorts of different techniques and trying to understand what's going on. So this is just me dropping a whole bunch of particles. I color them by their magnitude of the wind. So this is, notice the strongest winds near the surface are actually in this region behind the forward flank. So, and you know, I'm going to run a lot of this stuff. It's going to come at you. I'm not going to be able to, you know, I'm still trying to figure this out. But you can see this is, you know, there's a lot of convergence and then a lot of lifting. You definitely have a significant amount of vorticity being tilted and certainly stretched. So we're behind the gust front, the RFD, so this is RFD air. So I'm coloring it by velocity. So the strongest winds near the surface are right here. The winds are a little weaker over here. And here's the tornado forming, and here's that SVC. You can see there's two different circulations going on. I have more video that will sort of make this even clearer. But I'm showing this to you, and this is, by the way, no one else has ever seen this before. You're the first audience to see these pictures. Some of them, anyway. Other than my collaborators. So here's vorticity during what I call a maintenance stage. This is what we call the stage where the tornado's on the ground and pretty much churning away. There's the tornado. Here's a whole bunch of these. I first really focused on these little vortices here, but I think this SVC, this current of vorticity, is probably playing a more important role. But you'll see that the cyclonic vortices essentially just get ingested into the tornado, contribute towards its circulation for sure. We get these horizontal rolls. It just gets, you know, the updraft is so strong it just peels them right off the ground. You know, it goes on. A lot of stuff going on. So I'm going to try some trajectories now. The red one is where I place along the forward flank boundary, so you can sort of see how this evolves. And these guys I put in sort of in the FFD, RFD era. This is RFD era. So I'm trying to say, okay, let's try to see if we can build a conceptual model here. But what really intrigues me is this streamwise vorticity current really is like a thing. It's truly like, I don't know what to call it. It's like a weak-ish, tornado-ish thing that is generated from all the thermodynamic cooling. It's consolidated, lifted, and this is vorticity that is clearly, since it's streamwise, it's basic. So streamwise vorticity is vorticity that is it's aligned along the motion vector, so they're both pointed in the same direction. So certainly when you see this thing tilt upward, now it's vertical vorticity. It was horizontal, now it's vertical. Interesting, you know, we're trying to figure out where the air that gets into the tornado comes from. It seems that, at least my initial parcels here, show that a lot of the air that gets into the tornado core, not the downdraft in the center of the tornado, but like surrounding that core, originates in the cold pool. It's very clear to me. Not much of the air in the tornado seems to be coming from the warm side, which is interesting. It's harder to lift denser air than it is to less dense air. But when you have an updraft with 100 and something meter per second winds, maybe we can lift some cool air. Here's a view from like when you're standing on the ground, so it looks a little bit natural. There's the SVC, this is RFD air, it's kind of more chaotic. There's that little anticyclonic thing, and there's the tornado is the blue. So, you know, I've got the data on disk, I sit down and I make movies like this. And I'm learning as you are, essentially. I'm trying to figure this out. This is my technique for trying to understand, is to say, well, what's going on? So I'm trying a whole bunch of different things. In this sequence, the white parcels are in that sort of transition region, right where this, called the point of occlusion. And some of the parcels end up going over to the SVC side, and some of the parcels end up in the tornado. So it's almost like there's like a saddle point, is what always comes to mind when I look at this. I start to sort of kind of visualize this as sheets that are being sort of stretched into form. I'm still trying to figure out the best way to look at this. So now we have the same basic trajectory set. Now I put some vorticity in there too. In case you didn't know that was the tornado, you can now see it in the vorticity field. Again, just trying to gain some insight. The other nice thing about movies like this is I can show them to my, really seasoned storm chaser veteran friends and colleagues and say, can you, what's going on? Have you seen this in the field, et cetera, et cetera. So here's some really nice stuff where you can see this current. So this is what I'm saying when I see streamwise vorticity. So this is vorticity, and then we have the parcels that come in with that. So this long sequence goes for a while. When you see the volume rendered field here very strong, that means we've got vorticity. The tornado is happily going along, churning up things, and then just look at the SVC kind of goes away, but the tornado doesn't go away. So one of the interesting results so far is that you do not need this streamwise vorticity current to exist, at least not in its really strong phase, in order to maintain a very strong tornado. But look at that, there's that RFD surge that caused all that stuff to go around the tornado, and this thing kicks in again. Now this is late enough into the simulation where the tornado is not at its strongest. Okay, it's now in the EF4, EF4 range, maybe a little bit higher here and there. But it's interesting, it's a very dynamic simulation. There's a lot of things going on, but there's some things going on that I think we can probably come to some sort of conceptual model of what's going of the storm. So here again is that there's different ways of looking at it. I like this sequence because you can really see how everything's rotated. The vorticity itself, which is already kind of rotating, is consolidated, and the whole right there is probably the best, where you just see these things kind of turn over. Isn't that cool? And so it's the nice thing about visualizations like this is that they tell the story better than I can. You can sit and describe this in words, but it's easier just to show it on the screen. And I am spending a lot of time focusing on this feature because it's something new to me, and maybe it's something important. So I'm just dropping parcels along that boundary. This one probably shows it the best. There's no doubt in your mind that air is rotating, and there's no doubt in your mind that it's being tilted. And I'm fairly certain there's stretching going on. I just haven't analyzed it enough to say exactly to what extent is this vorticity being stretched by the updraft, which theory tells us it almost has to when you look at the configuration. Sometimes when the SVC goes away, what is the air doing? It's still sort of doing the same thing. It's just not, you're still the tilting and the rising here, but it's not as intense and it doesn't appear to be as organized. So, it's still going on, more of the same. Vorticity and velocity align perfectly. And notice that this circulation is separate from the tornado, and that's also interesting to me. So this SVC current, this streamwise vorticity current, is actually decoupled from the tornado itself. So it's providing vorticity to, say, the tornado cyclone, or maybe the mesocyclone, however you want to look at it. Now we're going to focus on the decay phase. So this thing does actually die. This is like the psychedelic disco tornado. Let's see what I mean in a second. It's pulsing, that's the bouncing around. But what you want to focus on is how fast it goes away. So it's still a pretty strong tornado, and then it's gone. Now this isn't necessarily what we expected. Here's vorticity, watching the same decay. Generally speaking, when you think of how a tornado dies, you think of it being undercut by the cold air, getting tilted, and it ropes out. This tornado fights to the bitter end, and then it just goes It only takes about 30 seconds to go from a pretty good tornado and then no tornado. So this is interesting. How do you communicate this? What's going on? Because this happens almost instantaneously along the entire length of the tornado. So here it's gone. And it dies with a very nice little downburst, which is nice. I study those. I still research on those too. This one probably shows it the most visually appealing. So there's the tornado struggling. This is the rain field, so you're seeing rain. And notice how it just gets engulfed in rain and it just gets pounded to the ground. And here it is at 6 times real speed. So there's the tornado. See how it's kind of wrapped in rain? I mean, it's been wrapped in rain a lot, but it's like really wrapped. And then it just kind of, it looks as if it's just this downdraft. Well, there is a lot of downward motion around the tornado. And it finally breaks that, whatever regime was holding that thing together, just finally falls apart. But it falls apart almost instantaneously, not instantaneously, but along its length. It's pretty amazing. And that, I just ended there. I think it was a 24-minute talk, so I think we're on time. But I wanted to leave some time for questions. So thank you for your attention.
We definitely have time for questions, so please ask away.
In your real image visualization of the tornado, so one of the first movies you showed us where, if you're a storm chaser, you're looking at the whole storm. I noticed that the mesocyclone itself pulses. Have you given that any thought?
Yeah, the pulsing thing, I don't think it's natural because it's so regular. I haven't done like an EOF analysis or some sort of analysis, Fourier analysis, but so the cloud field is being affected by the pressure field. If you think of the the LCL and all that, those things, the reason why you see a condensation funnel in a tornado has to do with the pressure being dropped, right? So the pressure's kind of going up and down, so you're seeing the same thing happen in the cloud field. It looks a little weird. It's not physical. I don't think it really affects the simulation much. But I think maybe it's because the updraft is so powerful, even though we're sort of trying to absorb those gravity waves at the top boundary, there's still some reflection going on, and we're seeing that. I still need to figure that out. It's a good observation.
How many hours did it take you to run that simulation?
How many hours? Okay, the actual model, the actual simulation ran on 20,000 cores. It's 20,000 CPU units. Blue Waters has like more than that. It has like 500,000. I'm going to probably try to use more for the next run I do. But wall clock time, it probably took about 2 days. But this simulation was restarted because you have to run from checkpoint files, things go wrong. It wasn't just like a nice smooth sailing thing. It was like, we had fits and starts. But yeah, it was like, I don't know, about 2 days of solid crunching, maybe 3. It's hard for me to actually answer that because the machine would sometimes have problems with disk and it would take forever to write some data. So it's a little bit sketchy, but that's supercomputers.
So they're always watching it to make sure they...
Mostly me. Yeah, get up at 5 in the morning. But no, it's okay. You can always restart files.
I was going to say, a lot of what you showed here really does make a lot of sense for field observations because one of the things we know, obviously, is that we want low LFCs for tornadoes, and so stretching, this idea of stretching is going to be very interesting, but we also know that we see the tail cloud develop a lot of times before these intense tornadoes. I wonder if that's a manifestation of this baroclinic stream on the forward flying.
I think it really might be. Because like you said, it suddenly makes sense.
Yeah.
When you notice though, the parcels themselves are traveling through the cloud. We humans see a cloud and we think of a thing, right? But like think of a lenticular cloud. Air is whipping through that cloud and the cloud itself is a figment of our imagination because the molecules are whipping through it. It's just that wave that's in the sky. And you see aspects of that in these simulations. So the tail cloud seems to be sort of part of that, but it's certainly when it gets tilted upwards, you don't see the tail cloud getting tilted upwards because you got the LFC or the LCL and you got condensation.
But even though that air is so much more stable, stretching is an important...
Stretching, yeah.
Then with that high vorticity, it wouldn't take that much.
It wouldn't take that much. So what I need to do is some like vorticity budget analysis, like in natural coordinates, long, and it's going to be fun because you got to follow the air and it's a pain in the butt. That's what I do.
Okay, so when you're talking about the horizontal rolls, you mentioned that you observed both cyclonic and anticyclonic vorticity with that. When there was the anticyclonic vorticity being fed into the updraft, were you ever finding that was weakening the storm or the tornado?
Yes. The anticyclonic vortices mess with the tornado. Sometimes it messes with it enough to weaken it. It almost strips away again, this is just my observation, but it sort of peels away some of that vorticity. And yes, that one event, that one anticyclonic guy, like really knocks, tornado really never recovers from that. So yes, there's definitely destructive interference. All right.
You can ask me more questions later.
Yep, I'll be here till after lunch.